Well, good morning. Thanks for coming out. I think we've got a great event here for our Mars Week Innovation event. My name's Melanie Saunders. I'm the Associate Center Director, and I am pleased to be here to introduce Andrew Chaikin, author, speaker, and space historian. Andy's here working this week with the JSC Engineering Academy to develop a course called Principles of Successful Spaceflight. So he's going to be here this week to help do some fine-tuning on that course. He's going to talk to us today about some of the challenges of exploration, not just technological hurdles, but more of the people side of things, the obstacles of politics and human behavior that we must get over just to be successful. And that's something that really resonates through me. I spent the first 15 years of my career here in the International Space Station, and I can tell you unequivocally, the hurdles were not at all technological. They were all political, people, culture, learning to work with international partners, learning to navigate a challenging congressional and administration environment through multiple administrations. So that's something that is very near and dear to my heart. He's also going to discuss some of the valuable lessons of the Apollo program and from the new recent New Horizons flyby of Pluto, and talk a little bit about how those the rewards that those discoveries bring. So I'll share a little bit with you about Andrew Chaikin. He is an extremely well-known, award-winning science journalist and historian. He's authored books and articles about space exploration and astronomy for more than 3 decades. He has been lauded by director, writer, explorer James Cameron as the best historian of the space age. He's best known as the author of A Man on the Moon, The Voyages of the Apollo Astronauts, and that's widely regarded as the definitive account of the moon missions. That was also the basis for Tom Hanks' HBO miniseries From the Earth to the Moon, which won an Emmy for Best Miniseries in 1998. His newest books are children's books, which I thought was an interesting foray into a new area for him, featuring experts from his conversations with Apollo astronauts. That's The Voices from the Moon, and Mission Control, This is Apollo, which is interesting in itself, and also because Apollo moonwalker Alan Bean did the illustrations for the book. He's also the author of Passion for Mars and many other acclaimed works, including many publications in periodicals. In addition to his career as an author, was the executive editor of Space and Science at space.com, and he was also the editor of their print magazine, Space Illustrated. He's also a commentator for NPR's Morning Edition and has appeared on many shows, including Good Morning America, Nightline, and the NPR programs Fresh Air and Talk of the Nation. And he's also been an advisor to us on space policy. A graduate of Brown University, he's also one of our own. He served on the Viking missions to Mars at NASA's JPL, and was a researcher at the Smithsonian Center for Earth and Planetary Studies before becoming a science journalist in 1980. So without further ado, a Renaissance man, Andrew Chaikin.
That's a nice title. Thank you. Thank you, Melanie. Thank you all. And it's always an honor for me to stand on this stage and talk to you folks and come back to the place where it all happens. And I feel especially good about what I'm doing this week and what we have planned a little later, early next year, with the JSC Engineering Academy to try and bring in some of the lessons of the history that are so valuable. I guess I should say I'm a historian and I'm here to help. Not a phrase you hear very often. But it really is true. It's amazing to me since I've been turning from, in fact, Glenn Lunny, the Apollo flight director and former shuttle program manager, is here. Glenn, very glad that you're here with us today. He said to me the other day that I was kind of like a writer who covered war stories, battlefield anecdotes, and I've switched from writing about the battlefield stories to writing about how you run an army. And it's a little bit like that. It's amazing to me as I've gone back with that lens to look at our past, to look at NASA's past, and say, not just what did we do, but how did we do it? and what makes the difference between success and failure. And that's what I'd like to talk about this morning. I'd like to give a shout out to The Martian, which I'm as anxious to see as I'm sure many of you are. It's great to see that we have another beautifully produced depiction of what could be in space. And I understand that it's like Gravity was, it's visually stunning, and thankfully, unlike Gravity, I think these folks have paid their physics bill. So I'm looking forward to seeing that. But you know, that is a great motivator for us, right? I mean, we go to these things, we're all space geeks at heart. I mean, we're here because we just can't get enough of this stuff. And we go to a movie like that and it just kind of feeds the fire, right? But the reality is that it's a tough journey to get from here to there. And I had another experience along those lines, or I had a window into that experience very recently, as a member of the New Horizons Pluto team. And I was and am very fortunate to be a member of the geology, geophysics, and imaging team for the Pluto mission. And what you see there is the middle of July, a bunch of us gathered around the laptops to see things that no human beings had ever seen before on the surface of Pluto. And you see sitting at the center there is the mission's principal investigator, Dr. Alan Stern, who's an old friend of mine. And Alan is really, as much as any single person, is the driving force behind that mission. I think it's fair to say that we would not have had a Pluto mission if it had not been for Alan's passion and commitment and intelligence. But everybody in that room and everybody on that project shared that passion. And we'll talk a little bit about that more in a minute. So this was really the peak moment, the big wow for us. And what we were looking at was this. And what you see here are mountains on the surface of Pluto that are 11,000 feet high. And they're made out of frozen water. On Pluto, the surface temperature is about 40 degrees Kelvin, which translates into minus 390 degrees Fahrenheit. It is cold. And it's so cold that water behaves like rock. And these mountains were pushed up by some process that we don't really know if we understand yet. We have ideas. And now we're seeing these features on Pluto that were just absolutely mind-blowing. They're just so stunning. And let's back out a little bit and show you the context of that. You can see over on the right here the full disk view of the side of Pluto that we flew past during the flyby, during the encounter. And the mountains are here, and they are within this mosaic down here. In the southern portion of a heart-shaped bright region. It was nice that Pluto greeted us with a bit of love. And we give it right back to Pluto. But you can see it's a remarkable landscape. It's got one of the more contrasty surfaces that we've ever seen in the solar system. Some of the darkest regions that we've seen in the solar system, right next door to some very bright regions. And there's an awful lot going on this planet. And I do call it a planet, by the way. I mean, it's got a moon, it's got an atmosphere, it's got geology. Come on. So this is the part of the bright area here. This very smooth plane, which we've tentatively called Sputnik Planum. And here's a view that I generated using the mosaic of the images wrapped around a sphere. And you can see that we're looking at, this is actually the northern boundary of that big plane. Again, this rugged area to the edge is the bedrock of Pluto. That's the frozen water mountains. But look at this almost completely featureless from a topographic sense. It's very smooth, no impact craters to speak of, which means that geologically speaking, it is very young. In fact, so young that we think it is still potentially active today. We see signs of glacial flow around obstacles here. You can see these flow patterns. And what are we talking about when we look at this vast plain? Well, this is not water. This is frozen nitrogen. It is so cold on Pluto that nitrogen gas, just like we breathe, freezes solid. And so does methane, and so does carbon monoxide. And so this sheet of ice is a mixture of some kind. We don't understand the proportions yet. It is a mixture of those three exotic ices: frozen nitrogen, frozen methane, and frozen carbon monoxide, forming that landscape. And apparently circulating in convection cells, which you can kind of get a hint of here, these cellular patterns, which continue out onto the plain, less contrasty, but still there. And it's kind of like a pot of oatmeal on the stove, where the heat causes the entire pot to circulate vertically and horizontally. And that's convective circulation, and we think we're seeing the same thing on Pluto. So when we saw all this, our mouths just hung open. It was just one of those great moments that is the reward for all the hard work. And I don't speak for myself about the hard work because I came in very late in the project. This is a project that has been in the works for a very, very long time. And even the mission itself, even the duration of the flying part of the mission has been longer than just about any other planetary mission from launch to the arrival at the first target. We launched in January of 2006, and it took 9.5 years to get to Pluto, which is 3 billion miles away. And that's close for Pluto. I mean, there are times when Pluto's at the other part of its orbit that it's more like 4 billion miles away. And so we are talking about, you look at this diagram here, the orbit of Jupiter is inside here, right? They're not even showing you the orbits of Earth and Mars and Venus and Mercury. You've got to zoom out pretty far to get a sense of how vast this area is that we're covering with this mission. So it took a long time to get to Pluto. That meant that we had to have a spacecraft that had onboard fault detection and analysis and quite a big degree of autonomy to take care of itself. It spent much of that flight to Pluto in a state of hibernation. And you can imagine that planning a mission like that, developing the hardware, developing the mission techniques and so forth, that was an enormous effort. Going out that far from the sun, just figuring out how to even gather the data when you got to Pluto, zooming past. And by the way, the New Horizons spacecraft left the Earth on an Atlas V. The spacecraft itself weighs about 1,000 pounds, and it's the size of a grand piano. It left the Earth on the biggest rocket we could get for it, and it left at 36,000 miles an hour. The Apollo astronauts took a little less than 3 days to reach the moon. New Horizons crossed the orbit of the moon in 9 hours. It was making tracks. And it had to get to Pluto in 9.5 years. And why was that important? Well, there was some concern that if we waited too long, Pluto would get farther from the sun and it would get colder, and its very, very thin atmosphere, which is mostly nitrogen, would freeze onto the surface and we wouldn't be able to study it. So I hate when that happens. So we really wanted to get there before that happened. Now, I've just told you about the mission itself, but the gestation of that mission goes back even further, because it really goes back, actually it goes back even further than this photo. This photo is 1993. These are some of the scientists who were at the core of the group that made this mission possible. And you can see Alan Stern here. And actually, it goes back to 1989, which was the last stop on the Voyager grand tour of the outer solar system. Remember when Voyager flew past Neptune and photographed this enormous blue planet and its moons, especially the moon Triton, which is a little icy world, much like Pluto. Of course, we didn't know what Pluto was like then. We assumed that we were seeing a world very similar to what Pluto must be like when we saw Triton. But that was it. That was the end of the grand tour. Pluto had been left off the itinerary. These scientists said to themselves, first Alan Stern said to them, and then they said to themselves, wait a second, why don't we have more to look forward to? Why aren't we going to Pluto? What about the rest of the grand tour? And they said, why not Pluto? Why not now? Why not us? And that's what started the effort. And they called themselves the Pluto Underground. And so, they were the ones who pushed to get a Pluto mission on NASA's radar. It was a long slog. There were concepts that were offered and rejected and offered again and rejected again and reworked. And it took a decade after this picture was taken before the New Horizons mission was officially a go. And at that point, they had to really get into high gear to create the spacecraft and the mission parameters in time for that 2006 launch, which, by the way, included a flyby of Jupiter to increase the speed. So that was the key element in that timing. Now, how did Alan Stern, as principal investigator, create a culture that would invite success on such a challenging mission? Just enormous challenges of a mission like this, and having to do it under a very short time span of preparation. What he did, and he and I had a conversation about this about a week and a half ago, before I came down here to prepare for this. And I said, tell me about some of the things that you did to enhance success. And he said, the first thing I did was I told the contractors, everybody involved, the people from NASA who were working on the mission, but especially the contractors who were going to design and build the spacecraft, I said, this is our Everest. Pluto is the Everest of planetary exploration. And we are the only ones in our lifetimes who have this opportunity to do this. We gotta do this. This is going to be amazing. But it's going to, as the Everest analogy implies, it's going to take everything we've got, all the persistence, all the ingenuity that we can bring to it. So that was key. Now, the other thing he told me was that aside from the challenges of the spacecraft and so forth, there's another human challenge with just the culture of the science teams. Because so often what can happen on a science mission is that you have groups of scientists that have been working on a particular instrument. Okay, one group has been working on a camera, another group has been working on an infrared spectrometer to analyze the composition of the surface, another group is interested in the atmosphere of Pluto, so they're more interested in the ultraviolet spectrometer, so on and so forth. There's a group that wants to study the particles from the sun and how they interact with Pluto's atmosphere and so forth, and that's the plasma experiment. And so you have these different areas of interest, and traditionally they would be grouped by what instrument they were associated with. And what does that lead to? It leads to stovepiping. And they didn't corner, science missions didn't corner the market on stovepiping, as I'm sure you all know. This is just part of human behavior. Just leave me alone, let me do my thing, I don't need to talk to anybody else. Somebody said it's like, You're all swimming in your own swim lanes, and you say, I'll meet you at the end. Well, it doesn't work that way, because a spacecraft and a science team are a system. And we have to think in terms of an interrelated system when we think about spaceflight, whether it's robotic spaceflight or human spaceflight. We don't have the luxury of saying, leave me alone, let me swim in my swim lane, and I'll meet you at the end. That is an invitation to problems and perhaps failure. Alan understood this. He'd seen missions where the culture was very stovepiped, where people didn't have access to each other's data. If the one team needed to know something from the other team's results, the other team was not allowing access. It was kind of like warfare on some of these other missions. So he stood up and he said to his science teams at the very beginning, we're not going to stand for that. We're going to be friends. We're going to be collaborators. We are going to group people not by what instrument they belong to, but what area of interest, what discipline. So we had science theme teams. We have a geology team, geology and geophysics and imaging. We have an atmospheres team. We have a composition team. We have a plasma team, and so on. And people from those teams may be associated with different instruments, but they're all together, and they all allow the other teams to see their data. And I noticed, even in my limited time working with the teams during the encounter, I had people say to me, you know, this is an amazing culture on this mission. It's really collaborative, it's really open, it's really great, the camaraderie is great, and it was a joy to be around them. So here you see Alan and several of the scientists from different teams, you know, and you can tell that there is that spirit. Now, Alan, you have to understand, like me, we're about the same age, is a child of Apollo. And he grew up, as I did, at the same time that the space program was growing up. And, you know, I can just tell you from my own experience, I waited anxiously for each new copy of Life magazine to come in the mail with the pictures from, you know, Ed White's spacewalk. That changed my life, okay? The summer I turned 9, to see Ed White on the cover of Life magazine with those incredible pictures of the first US spacewalk. I was building the Revell model kits of the Apollo spacecraft and so forth. How many of you built model kits of the, yeah, that's what I'm talking about. We all wanted to be vicarious participants if we could. We all wanted to be part of the adventure. We were completely sucked into it and electrified by it. And Alan was the same way. And so he wanted, as much as anything, for him, in his mind, the Pluto mission is a way to recapture the experience of exploration that we had during Apollo. The experience of exploration, and I always like to use two words, exploration and discovery. You have to have, if you don't have discovery, it's not really exploration. You've got to go somewhere where nobody's been, see things that nobody has seen, learn things that nobody knew. That's what it's about. That's what enriches us. That's what elevates us. That's what makes all the hard work worthwhile and inspires generations to come. So Alan understood that instinctively. And you know, that program that we call Apollo changed a lot of people's lives. And it still is changing people's lives. I mean, I meet people who weren't alive or were not really conscious when this picture was taken of Buzz. And by the way, did you ever notice, I've blown it up here so you can see this. We all know that's Neil taking the picture. But did you notice that the Earth is in the visor? You can even see the blue tint of the Earth. It's kind of an amazing little portrait here in Buzz's visor. That experience changed the world, and it changed many, many lives. And at the heart of Apollo's success was the fact that everybody who worked on Apollo, and at one time the estimate was 400,000 people around the country and even internationally, all of those 400,000 people understood what the mission was. And it boiled down to man-moon decade. Kennedy had said, put a man on the moon, bring him home safely before the end of the decade. That's it. It's the clearest and most compelling mission statement you could ask for. And as it turns out, it's the clearest mission statement, the most compelling and clear mission statement that NASA has ever had in its history. And that's why I keep going back to Apollo, because Apollo is as close as we will ever get to a perfect program. It was the one time in our history when space was not only exciting, but of national importance in terms of national security, national prestige. It was vitally important that we win the moon race as part of the context of the Cold War. Okay, space had become the new battleground of the Cold War. So we went to the moon not because John Kennedy woke up one morning and said, by God, we are a nation of explorers and the moon is out there waiting for us. No. He woke up one morning and somebody told him that Yuri Gagarin had become the first human in space, and he'd been embarrassed also by a little fiasco called the Bay of Pigs, and he realized in very short order that we had to do something dramatic to show the world the strength of a free society, as opposed to the Soviet Union's communist society. So that's where that came from. And the amazing thing about Apollo is that we didn't stop with Apollo 11. We didn't quit after we satisfied Kennedy's challenge. We went back to the moon several more times. We landed on the moon a total of 6 times. And by the last 3 landings of the Apollo program, you had 2 guys, in this case Dave Scott from Apollo 15 and Jim Irwin, who took the picture, not visiting the moon, but living on the moon for 3 full days, taking moonwalks as long as 7 or 7.5 hours, a full working day out on the surface of another world, and driving a battery-powered car for miles across the landscape, even up the sides of lunar mountains. They went up this mountain, hundreds of feet up, and found rocks almost as old as the moon itself that let us reach back in time to the earliest history of the solar system. Wow, that's icing on the cake. And then we quit because the budgets didn't stay the way they had been in the mid-1960s when we were building the VAB and the launch facilities at the Cape, and we were building JSC, and we were developing the expertise to build the Saturn V and the Apollo spacecraft and so forth. When we did it, that mandate was no longer there and the budgets declined. And that's not because the world is an evil place and wants to hurt the feelings of space fanatics. It's because it was done for political reasons to begin with. So the challenge has changed, but the lessons of Apollo still apply. And I love the story that Max Faget told me. Now, those of you all should know who Max Faget was. Max was the engineering mind, the chief engineering mind behind the design of the Mercury spacecraft, which became the same shape as the Gemini spacecraft, and also the Apollo command module and the shuttle. So Max is kind of the chief spacecraft designer of NASA in the early days of NASA. Well, one day in the 1970s, Max and Bob Gilruth, who had been the center director during those formative years and was really responsible for creating the culture of JSC, they were walking on the beach at Galveston. There was a big full moon up in the sky, and they were walking along the beach and looking up at it. And Bob Gilruth said to Max, someday people are going to try to go back to the moon, and they're going to find out how hard it really is. And the more I've dug into the history with a standpoint of trying to extract the success principles from that history, the more I've come to understand that what Bob was talking about was the human side of it. Because it isn't enough to do superb theory and design and turn those designs into a plan to build something and have a mission plan and all that. You don't get from you don't get from A to B without taking into account the human element of the program. And it's hard for engineers to understand that sometimes because engineers don't do people stuff. Not by nature, anyway. But the fact of the matter is that it's not just about the rocket science. And in fact, you look at this picture. This is the launch of Apollo 11, and here you see in the center here, George Miller, who was the chief of human spaceflight at the time. It happened to be his birthday, July 16th, 1969. Standing next to him, of course, is Wernher von Braun, who was the director of the Marshall Space Flight Center. And, you know, Miller had come to NASA headquarters in 1963 and had seen, his advisors had told him, there's no way we're going to get to the moon by the end of the decade. You know that, don't you? And as he dug into it, he realized that one of the biggest obstacles was the very conservative test flight schedule that von Braun and his people at Marshall had set up. And they had their own culture, which was a very methodical and very hierarchical culture, a very methodical approach to test flying. They wanted to test the Saturn boosters, adding one live stage at a time. So you'd have, let's say, a Saturn V, and only the first stage would be a functioning first stage. And there'd be 2 dummy stages on top of it. And if that worked, you'd say, oh, good. Let's add a second stage that's functional. If that worked, you'd say, oh, super. Let's add the third stage. Well, some very smart people, including a guy named Joe Shea, who later became the manager of the Apollo spacecraft program down here, looked at that and said, you know, this is flawed reasoning. You're not reducing your risk with this plan. You think you are, but you're not flying enough to be statistically significant, so you're really not establishing a reliability model with so few test flights. That's number one. Number two is, let's say the first stage does work the first time. Well, you have an opportunity to do more than you planned. You're not in a position to take advantage of success. So Miller was totally on board with that, and he decided that the very first Saturn V would be launched with 3 live stages. It was called all-up testing. If you see that in any of the accounts, look it up and read about it, because it was one of the key decisions that made it possible to get to the moon by the end of the decade. Now, was von Braun happy about that? No. In fact, he fought very vigorously against that decision. But Miller was essentially a czar. And he said, I'm sorry, you don't have a choice. And that's the way it was. Now, the other thing that Miller did that has real relevance for what we're talking about is he brought in a fellow here on the right named Sam Phillips, who was an Air Force general and had been the director of the, I believe it was Minuteman, and had run some of the big ballistic missile projects for the Air Force. And before Apollo, those were really the biggest, most complex engineering aerospace projects we'd ever seen. And you know, when you're talking about a missile, everything in that missile is intimately connected because of the environment it's in, the shared environment, the vibration environment, the RF environment, all of those things, the thermal stuff. All of those things mean that you don't have the luxury of just staying in your swim lane. You don't have the luxury of just thinking about your piece. because some piece over here may be affected by the way your piece operates, and vice versa. So you need good systems engineering and good systems management. And that's what Sam Phillips helped to bring to NASA for Apollo. And did everybody welcome him with open arms? No, of course not. We are basically tribal creatures, right? I mean, when you think about it, and this is not because we're bad, it's because we're human. We're wired up to be tribal creatures. And the first reaction, including many people down here, was, we don't need some Air Force general telling us how to run our program. Thank you very much. So it took a while for Sam Phillips to get the message across and get the methods integrated into how we did business. And also to get the kind of oversight from headquarters that they needed to keep track of problems in case they could help resolve them. They didn't, none of the centers wanted headquarters looking over their shoulder. Anyway, all of this is to just give you a little taste of the human challenges that existed even back then during Apollo. And I'm sure if you think about it, it's not hard to think of ways in which the environment today reminds you of that. I'm not going to spend a lot of time on this. This is what I'm going to be teaching in the class. This is what I call the Apollo Pyramid of Success. And these are the success principles that I've extracted from the history. It's kind of a work in progress. In fact, Glenn said to me, don't show this to people and give them the wrong impression that this is just a recipe, that if they just follow these steps, they'll be good. And he's absolutely right about that. So every one of these steps, whether it's the systems thinking we were just talking about, or it's what-if thinking, which is what you do when you try to anticipate what can go wrong and what you'll do in those contingencies, all of those things, you've got to constantly evaluate your progress, your methodology, and say, is it working? So we're going to go into this in much greater detail, but I just want to talk about a couple of these success principles. We've already talked about the fact that we had the clarity of the goal in Apollo was very important. The leadership, Bob Gilruth was a superb leader, and he created a culture that just gave people the room to be their best. In fact, Glenn, this is not by design, but you're kind of the star of the show here in some ways with the quotes you've been giving me, but you see here Bob Gilruth and Chris Kraft and George Lowe, three of the great leaders of Apollo. And as Glenn said, as a bunch of 20-something flight controllers and later promoted to flight directors, he said we were all in awe of what our leadership allowed us to do. And that is the key right there. He said we felt trusted. And in the return, we gave the best we could give. And it was an amazing experience. So superb leaders, that's an element of a superb leader right there. Understand the environment. That's one of my success principles. Well, in the case of Apollo, when Kennedy got up and said, we're going to go to the moon, we had exactly 15 minutes of human spaceflight experience under our belt. And it wasn't even an orbital flight. It was a suborbital flight. And now Kennedy was saying we were going to have to go to the moon. And very, very soon it became clear that the things you had to do to go to the moon and come back were way beyond anything that we were going to have experience with anytime soon. And so a new program was created called Gemini. And one of the most important goals of Gemini was to demonstrate the ability to rendezvous in space. Orbital mechanics is tricky stuff. In fact, some of the early astronauts found out just how tricky it was when they tried to fly rendezvous, and they ended up not going where they thought they were going to go because orbital mechanics is not intuitive the way flying an airplane is. When we accomplished this rendezvous in December of 1965 between Gemini 6 and Gemini 7, as depicted here in this beautiful artwork by the late Paul Calley, one of my heroes, that was the moment when we really pulled ahead of the Russians in the space race, because they were not even close to doing this and would not be for another few years. So understand the environment. Sometimes that means you've got to actually go perform missions that will tell you about the environment you're going to be operating in. Out-of-the-box ideas can win. Well, one example that you've probably all heard of is the lunar orbit rendezvous technique, which was kind of a dark horse for a while and was resisted for a while when it was first championed by a fellow named John Houbolt from Langley, but ended up becoming one of the key decisions that allowed us to go to the moon. But another out-of-the-box idea, and you may not realize this, the first flight around the moon, Apollo 8, was not in the original schedule. The original schedule called for Earth orbit test flights. And you'd do just the mothership, the command service module in Earth orbit. Then you'd launch the command service module with a lunar module and fly that in Earth orbit. Then you'd fly it a little higher in Earth orbit. You kind of, very manageable steps. And then you'd take the whole show to lunar orbit for one last rehearsal, and then you'd go, the next mission would be try to land. Well, that was the very methodical plan that they had come up with. In the summer of '68, they realized the lunar module was so far behind schedule that that was going to screw up the entire plan, and it was going to delay everything, and time was rushing by. And so George Low had a brilliant idea, which was to say, look, I know this isn't what we planned, but let's take the second test flight of the command service module and send it around the moon without a lunar module. And we'll learn so much from that that it'll be a giant step ahead. And, again, Glenn had a great line about this when we were talking the other day. He said Apollo 8 shocked the system because people had gotten into the mode of, we have a plan. We know what we're doing. What's this crazy idea? In fact, the NASA administrator was in Vienna at a conference, and when his deputy, Tom Paine, called him up and told him this idea, he pretty much yelled over the telephone, "Are you out of your mind? Don't you know you're putting the entire agency at risk?" But he calmed down, and he saw the wisdom of it, and that's what they did. And that's why we had that unbelievable moment at the end of 1968, that very divisive year for this country, when we'd had assassinations and riots and demonstrations at the political conventions and growing dissent over the war in Vietnam. All of that was tearing the country apart, civil rights. And at the end of the year, we get this transcendent moment of hearing human voices coming to us from another world, orbit around the moon, and seeing the planet as a celestial body for the very first time. Now, this is Glenn in the center here, Apollo 13, the rescue of Apollo 13. You've all seen the Apollo 13 movie. I hope you have. It's a pretty good movie. It's very focused on the activities in mission control and the real-time ingenuity that was applied to saving those guys' lives. And that's a wonderful story. But one of the things that doesn't get talked about as often is the fact that all of that real-time ingenuity was built on a foundation of what-if thinking, what I call what-if thinking. And what-if thinking is what you do anytime you sit down and you write a contingency checklist. It's what you do every time you sit down and you're creating a simulation exercise where you're going to throw malfunctions at the mission control team or the crew, see how they react. And you do it in the design stage. And they did it in the design stage. When it came to the lunar module, in fact, this was Joe Shea, said, after he came down to Houston and started running the Apollo spacecraft program office, he said, you know what? I want the lunar module to be able to propel the two spacecraft together with its engine in case the engine on the mothership conks out. That meant the docking system had to be strong enough. That meant that the attitude control system had to be capable of keeping the craft steady with the impulse coming not from the big engine over here, but from the lunar module's engine. And that turned out to be a very important decision, years before Apollo started flying. So they ended up having to do that to get back on the right flight path on Apollo 13. You may remember from the movie that at one point the computer was powered down. They had to do an alignment to get back on the right trajectory with a small engine firing. They didn't have the computer, so they used their gun sight, which is normally something you use during rendezvous. They used it to sight on the Earth, and by placing the horns of the crescent Earth right on this crosshair and bisecting the crescent with the other crosshair, they would be in the right alignment to do the burn. Amazing procedure, right? Very, very cool example of using what you have available, which of course is what The Martian is all about. But it didn't come out of nowhere. In fact, it had been thought up, as a contingency procedure for Apollo 8. Same thing with the much celebrated CO2 scrubber that they built on board with instructions from the ground on how to take a air purifying canister from the command module and adapt it for use in the lunar module. That too had been inspired by an Apollo 8 simulation. So what if thinking pays dividends amazingly. Now, even if you do everything on my success pyramid, it doesn't mean you're home free. Because as we've been talking about, we have pretty much hardwired into us a set of behaviors that are completely unconscious, that can invite failure. And they're things like hubris and complacency and groupthink and not invented here, which is basically a tribal behavior. It's like, how can that idea be any good? It came from those guys. Non-communication, blind devotion to rules or worldview, and resistance to change. These are not, NASA doesn't have the market cornered on any of these things. Engineers don't have the market cornered on any of these things. This is throughout humanity. This is basic. And again, we don't do these things because we're bad. We do them because we're human. But the lesson of spaceflight is it's so hard. It demands so much of us. It is so unforgiving an endeavor that we have to rise above these very basic human behaviors in order to succeed. And I'm going to give you just one example of the ways in which those behaviors can invite failure. At the very beginning of the Apollo program, we did not know how we were going to go to the moon. And I just mentioned Lunar Orbit Rendezvous was the one that was chosen, but it was a while before they figured out whether they wanted to just go directly to the moon with a huge rocket that would have been even bigger than the Saturn V, or maybe launch two smaller rockets, maybe two Saturn Vs, and assemble the moon ship in orbit, Earth orbit, before you go out to the moon. There was even one version of that called for refueling in Earth orbit. I mean, we haven't done that yet with a human spacecraft, never mind doing it in the 60s. And then finally, they decided on Lunar Orbit Rendezvous. But that decision was not made until the middle of 1962, a year after the program began. Well, in the meantime, there was so much intensity. There was so much urgency. Kennedy had gotten up before a joint session of Congress and said, we've got to do this by the end of the decade, and that this was something that would show the world the greatness of our society. Well, NASA and the prime contractor for the spacecraft, North American Aviation, took off running. And they started building stuff, even before they really knew what it was going to have to do. So they were not following the all-important need to define proper requirements. Okay? And the result of that was, as their chief engineer at North American said in an oral history interview just a few years later, no one really knew what we were designing, including ourselves. Well, you move forward to 1963 when Joe Shea comes down here and he sees that even now, and this is more than 2 years after the start of the program, they still haven't designed a command module that can accomplish the docking with the lander. It's not suitable for the lunar mission. Every spacecraft that's coming off the line is different from the one before because they keep thinking of improvements and they keep kind of adding them as they go along. So your whole hardware heritage is being thrown out the window every time you make a change, and it's going to cost you money to re-verify and so forth. So it was a mess, and he froze the design and said, okay, this thing that we've been building is just going to be for test flights. We're going to call it Block 1, and then we're going to do a proper set of requirements for the actual lunar spacecraft that we're going to call Block 2. But in the meantime, this Block 1 spacecraft had to be created and used for the first Apollo test flights. Now, the contractor, North American, was arguing for certain things that they were thinking would make the spacecraft safer. They wanted a hatch that could be jettisoned with an explosive bolt in an emergency. I mean, that's what they had on all the aircraft that they had built. That's what NASA had on Mercury, in fact. However, the second suborbital flight on Mercury, Gus Grissom's flight, Gus almost drowned because his hatch blew off prematurely. And NASA decided there's no way we're ever going to do an explosive hatch. And they said, we're going to have a hatch that opens into the cabin so that it will be sealed, held shut firmly by the cabin pressure. And when they made that decision, they started down the road to a real problem. Now, one of the other decisions that contributed to that was the decision to use pure oxygen as the atmosphere in the spacecraft. Now, there was a very good reason why they felt they had to do that. North American was arguing, no, we should use a mixture, nitrogen and oxygen, because it reduces the risk of fire. But we didn't have the technology to monitor the relative amounts of oxygen and nitrogen with enough accuracy to make sure that people were going to remain healthy in that mixed gas atmosphere. And so there was literally a meeting in the summer of 1962 when the head representative from NASA at the meeting said to his counterpart from North American, "You're the contractor, you will do as you're told, period." And that gives you an idea of the tension in the relationship at that time between NASA and the prime contractor that was building the Apollo command and service module. So the decision was made to use pure oxygen. Now in space at 5 psi or 4.5 psi, there is a fire risk, but it's nothing compared to the fire risk when you're on the pad and you're pressurized slightly higher than atmospheric, because you've got this inward opening hatch and you need to maintain a pressure inside the cabin relative to what's around you. So they were actually pressurized at a little more than 16 psi, pure oxygen. Now that is something that most people have no experience with. But there was a flight surgeon at North American, a guy named Toby Freeman, who argued vigorously because he had seen a flammability test and he knew the results of having pure oxygen at high pressure. But it was not listened to. Now we move ahead. We've got a spacecraft being prepared for the first Apollo flight, Apollo 1. And here it is on the assembly line in 1966 at North American. And look at all these guys climbing in and out of the spacecraft working on it. What you can't see in that picture is the inside of the spacecraft, where there are very thick bundles of wire snaking along the floor of the spacecraft cabin. And the technicians, even though they're trying to be as careful as they can, they just cannot avoid damaging the insulation on some of those wires sometimes. And they try to keep track of it, they try to fix it, they try to maintain the integrity of that wiring, but it's impossible to do that perfectly. So you have a process in which the risk of fire is actually being increased as these guys do their daily work. Now, I put this quote up here from a contingency plan that NASA wrote in 1963 that says fires in the spacecraft must be avoided at all costs. That should have been on a banner in every factory, every conference room, every environment at NASA, so that it never slipped off people's radar. But it wasn't. And it was easy to become complacent because we'd had success with pure oxygen on Mercury and Gemini without any problems. And then in January of 1967, we paid the ultimate price with the first Apollo crew, Gus Grissom, Ed White, and Roger Chaffee, dying in a flash fire inside the command module. And this is a flammability test that was done after the fire, in the weeks and months after the fire, in an identical command module at 16 psi pure oxygen. And it was just a conflagration. It was just unbelievable how intensely flammable things become when they're sitting in pure oxygen at high pressure. And this quote says it all. George Miller, 1 month after the Apollo fire, basically saying, look, we had been operating with this condition during Mercury and Gemini for years, and the success that we had in those programs demonstrated that the possibility of fire in the spacecraft cabin was remote. And I submit to you that that is flawed thinking. That is not a valid conclusion. That is what we did again and again with the disasters that we had in Shuttle, which basically boils down to saying, well, it hasn't bitten us so far, so we must be okay. And again, this is basic human behavior. There's research that shows that close calls actually increase the likelihood of a real disaster down the line. So this is a cautionary tale. Now, we recovered in magnificent form. Nobody recovers from disaster like NASA. I mean that. I mean, there's just absolutely stunning. And in the amount of time that they did recover, led by George Low here on the redesign of the spacecraft, this is the Block 2 spacecraft, the one that had the proper requirements written for it and proper principles of systems engineering applied to it and systems management. And you can see it has a one-piece hatch that can be opened very quickly. It has been made fireproof. There's a whole bunch of other problems that were fixed with the opportunity that, unfortunately, the fire provided. And this is the spacecraft that ended up flying all those amazingly successful missions. And so the discipline and the focus that Low and his people brought to that process was just stunning. And it just was like rocket fuel to propel NASA to the moon. Now, the other piece of this, the people piece of this that I find very compelling, is symbolized by this quote from one of the engineers from North American. We were all saddened by what happened, and it wasn't North American aviation anymore. It was, we're a member of a team to get the job done to get to the moon. And badges became academic. There were not any badges anymore as far as I was concerned. So what we're saying is that as terrible as the fire was, it opened up an opportunity for people to rise above their basic tribal nature. And by doing that, transcend those basic human tendencies to make it possible to succeed in this most demanding of human endeavors. Now, since Apollo, one of the problems that we've had is that these planks on my Apollo success pyramid have not all been there. The goal has never been as clear as it was for Apollo. We never have had the amount of resources that we need when we did shuttle and station. On and on and on and on. So We've got to recognize that situation and go in with our eyes open and recognize that when we have holes in our success principles, we are more vulnerable to those failure behaviors I showed you. And so it requires constant vigilance, constant self-examination. You know, if you're not waking up in the middle of the night saying, what have I missed? You're not doing it right. And there's a quote from a former flight director, Tommy Holloway, you're not as smart as you think you are. And that's one of those things that should be on every conference room throughout NASA. And that would be a productive thing. We want to realize that spaceflight is a high wire act. You're always on the high wire. And one false step and you can plunge to your death. And if you were literally on a high wire, you'd never get complacent, right? But it's hard to keep that focus sitting in a conference room here at JSC. So the challenge is, and this is the challenge that we're going to talk about in the JSC Engineering Academy, is how to increase our own awareness and to reinforce that awareness with a culture that promotes this kind of vigilance and this kind of openness. It's a balance between ego and humility. Just like a high wire walker has to maintain balance, we have to maintain a balance between our ego, which we've got to have or we wouldn't even try to do this stuff, with a sense of humility and openness and a very keen awareness of Tommy Holloway's phrase, you're never as smart as you think you are. And I sum all that up. To me, the lesson of Apollo is in the huge group endeavor that is spaceflight, human nature is as critical as engineering principles. Neither can be ignored without inviting failure. And so, are we there yet? We're not there yet. But if we really keep our eyes on the prize, I think we'll get there. Thank you. Now, I'm not sure if we have time for Q&A, but if we do, I'm happy to. And if we have a mic, I think we do have a mic. Two quick questions. Yes, sir.
NASA doesn't seem to be in charge of its goals. They're defined by other entities that change them every 4 to 6 years.
Right.
How do we deal with that?
So the question is, NASA's not the captain of its own fate in terms of setting its goals. And that, unfortunately, is a harsh reality of the world we live in. NASA's an executive agency, and it can't chart its own course. It always has to take its orders from Washington. I don't have an answer. I don't really have a comprehensive answer for that, except that I would liken it to the business world, where you'll never have the luxury of operating 5, 10 years from now the way you're operating today. You've got to constantly reinvent yourself. I have to reinvent myself, right? The book business is kind of tough, you know? That's one of the reasons why I'm doing this, is because, hey, this is a great place for me to put my energies. So you've got to think in terms of how can we reinvent JSC? How can we adapt to an environment that is not like what we would have wished, what we were used to? And I don't know how you do that. I don't know what the answer is about what the new way of doing business is, but I know that if you're not open to that and if you're not trying to innovate, you won't get there. One more question? Anybody? Yes?
You're going to teach the course on how to do this starting in February. You're going to write the textbook for it. And how do I get my name on the waiting list for it?
Well, well, that's all right. Well, Paul, you'll be in direct contact with me since we know each other. And this is Paul Brady, who worked on Bailey, who worked on the MMU, and we've talked about that wonderful episode. The book will take a little while longer than the class. It's a work in progress, although I'm trying to keep my eyes on the prize and get it done sooner rather than later. But it will be something that will be available to everybody at NASA. Everybody will know about it. I won't keep it quiet, I promise. Thank you all so much. I really appreciate it, and I look forward to coming back at the beginning of next year and maybe seeing some of you in the class. Thank you.
So thank you, Andrew. That was an amazing talk. We wanted to give you a little token of our appreciation for your efforts on our behalf. This United States flag was flown on December 5th, 2014, on Orion's EFT-1 test flight, and it flew 63,000 miles and reached an altitude of 3,606 statute miles.
Awesome.
So, with our appreciation for your efforts.
Thank you
very
so much. I really appreciate it. Thank you. And it just flew another few feet. Okay.
There we go.
All right.
Thank you, everyone.